Hi, I'm Mark from Undo, and I'm going to show you how to reanimate a zombie using time travel debugging. First of all, we're going to need to capture a zombie, and to do that, I'm going to run Doom, Chocolate Doom with the original shareware iWAD under LiveRecorder, which is Undo's software recording program. So here we are in Doom. Let's get started. And now I'm in a spooky space base, I guess. Things don't look very clean. That looks a bit scary. We can look out the window. But I'm going to run along here, down this corridor, see what we can find. Ah, a door. Well, there's probably nothing horrific behind that, so let's open it. Oh no, it's zombies. Wouldn't you just know? Now, these zombies, rather unfairly, seem to be armed with guns, but fortunately, I can fight back. So that's one taken care of, and another one. Well, I'm not sure the world is safe, but this will do for now. And I've recorded enough of this, so I'm going to stop. What we're doing here is we're saving out from LiveRecorder a machine instruction precise trace of absolutely everything that program did. Every value, every line of code. And you could even step through at assembler level if you want. What we're going to do is investigate what happened when that game was running. So I'm going to load it into UDB, our time travel debugger, and we're effectively creating a zombie of our own here, because it's actually going to reconstitute all of the guts that we recorded in our recording file and give us something that we can debug and inspect as if it was the original process. So let's first of all jump to the end of time and we'll see how things look. Using the power of GDB scripting, I've actually added some commands here which will allow us to dump the internal frame buffer of the software. So if I just load that in, we gain access to the Doom show frame command. If I run this, what it's going to do is dump out a PNG of what was in Doom's frame buffer. We'll be able to take a look at it just as if we were still there. And what we can see is, yeah, that looks like my final screen in the game. 91%, not my best for this particular battle, but it will do. And we can see here the two zombies. Now, if we look at the coordinates in the bottom of my paint program, you can see that we're at 195, 122. So that's X, 195, Y, 122 within this particular frame buffer. The nice thing about original Doom is it has a linear frame buffer. So you can take the base address of the frame buffer, which just appears as an array in the source code, and we can type in 195 for the offset in this row, plus 122 times 320, because it's a 320 by 200 viewport, and we can print out the value of this pixel, or if I've got an off by one error, a pixel quite nearby. Let's not worry about that. Instead, let's ask ourselves a question. How did this pixel get there? What code was responsible for it being set? Well, we can answer that using the last command in UDB, which allows us to query backwards in history and find the most recent time that value changed. So here we are, we've run back in time. You can see, instead of being at the end of recorded history, we're now 99% of the way through. And what's going on here is that we are in the rendering routine of Doom. So it's rasterizing stuff out to the frame buffer, column by column by the look of it. And what we can see is we're somewhere in the sprite drawing code, which makes sense because we started out wondering how that zombie sprite got there. I can reverse finish up this particular call stack, and that gives us the opportunity to understand how things hang together. So when I'm reverse finishing, I'm actually popping frames off the stack. I'm running backwards to before the function was called. And I can recover back to this function our draw sprite. I guess R stands for rendering. And we can inspect this little sprite object that's sitting in the arguments to this function. We can see, okay, this has got some coordinates in the game world. It's got textures. It's got something called a patch, color map. What I might then say is, well, okay, I want to know how this sprite really got here though. So what actually decided it was going to appear at this point in my viewport? Well, what we could do here is repeat our same trick again, but this time we'll look inside this structure and see who's been assigning to it. So we'll look and see who set the X coordinate in this sprite structure. we find ourselves further back in time again, no, 97% of the way through history now, in this function rProject_sprite, which is part of this whole rendering code. It deals with the binary space partition trees, which Doom uses to provide its pseudo 3D view. And this is projecting a sprite from an object called thing. Thing is some sort of representation of internal game objects. And actually, you can see here, this is representing our zombie itself. So the zombies are called monster type possessed. You can see this is a possessed. That sounds good. You can see its original spawn point. You can see what direction it was planning to move if I hadn't shot it. And you can see as well its health. And that is not looking so healthy because I won this particular scuffle. But what if we then want to say, well, actually, how did that health get updated? What happened there? We can use our last command again. And we can run back in time to the exact moment that its health went below 0. And if we look here, it used to be 5, now it's -5. The zombie's not looking so happy. And we are actually in the code for handling damage infliction, which is within the shoot code, which just makes sense because I used a gun. So let's double check what was on the screen at this point in time. We're expecting a not very healthy, but still alive zombie. Let's see what we get. And yep, he's got better. So that's it. We've travelled back in time. We've reanimated a zombie. My health doesn't look any better, but I understand that part of the Doom source code.